Okay, so I'm basically moving on from Andy here. I've got a couple of sort of introductory slides, and then we'll go into how you actually do data analysis and stuff. So some of this Andy touched on. He mentioned we're in a low Earth orbit. It's about 90 minutes rather than 96 now. I mean, it started off at 96 and it's somewhere between 90 and 96 because of the orbit getting lower. So we go around the Earth about every 15 times a day. So the reason this is important is that if something's in low Earth orbit, it can't observe targets constantly because the Earth gets in the way. You know, you're going around the Earth and you might want to look at something, the Earth gets in the way, you obviously have to stop observing it. So theoretically, we could observe a target for a maximum of about 2.5 kiloseconds, but we don't do that for spacecraft safety reasons. The longest we observe something continuously is 1.8 kiloseconds or half an hour. So one of these continuous pointings we call a snapshot. Observations can be made up of multiple snapshots. So if you're expecting more than 1.8 kiloseconds of data, you'll get a chunk, then there'll be a gap in time, and we'll go back to the target and then a gap. And so when you see an example event list, we'll see it later, but there are typically gaps in between the times we've collected data. So this can seem confusing until you're used to it, but it's very easy to handle, really. So in general, we have online visibility checkers. So this is planning it, assuming you're all going to want to rush off and ask for target of opportunity requests from Swift. So anybody can ask Swift, if you have a good scientific reason, you can ask Swift to observe whatever your target of interest is. And you have to fill in a form and this, that, and the other. But we have ways to check whether sources are visible. So I've just put these up basically for background knowledge, because we often get requests for people saying, can you look at this? No, it's behind the sun. So so those of us who work for Swift putting these things into the schedule and organising it, we either act as observatory duty scientists, so I'm one of the ODSs. We have the science planners who actually make the plans, and we do grumble a bit when we get asked to look at things that are behind the sun for the next 3 months or whatever. So we're never actively rude to your faces, we just curse you behind your backs, just so you know. Andy mentioned bright optical sources that we can't look at with UVOT. Well, that's not the only problem with bright sources. If something is bright in the optical, all the optical photons will pile up, and if you add them all together, it actually goes over a threshold where they appear as a low energy X-ray instead, if the CCD has not read out quickly enough. So we refer to this as optical loading. If we look at a source, so even if UVOT is blocked, so we're not collecting useful UV optical data, we still get these optical photons coming through, and they can appear as spurious X-ray sources. So if you're looking, but you think, oh, there's this new source, maybe it's detected in X-rays. A nova, for example. Novae are often very optically bright when they first come along, and we don't know whether there'll be X-ray detections. So you want to look for faint X-rays, and if it's a really bright optical source, you might think you've got one, and actually it's just this so-called optical loading. So it's something you have to be really careful about. But it's basically, the source is brighter than about 10th magnitude, you have to be wary. And at that point, we would use the window timing mode that Andy mentioned. So this is for the one-dimensional mode. We'll see a picture in a minute, because that's read out more quickly, and therefore there's less time for the optical photons to add up together to appear like an X-ray before they're read out. So I'm not going to go into this in more detail now. If any of you have thought about this and have questions, feel free to ask us later, but it's there for background information. Slide here just about how one can get the Swift data. So you've had an email from Paolo pointing towards one of the places that you can get the data. We obviously tend to recommend that you use the Leicester site, but we're in Italy, so you could use the Italy site, or you could even use the Gehrels site, but that's sometimes a bit slower, honestly. But the observations that Swift does, the data are downloaded quickly. So we have, not sure, a whole number of ground station passes, ground stations around the world. So we have our main Swift one is in Malindi, off the coast of Kenya, and it's actually operated by ENAF. So we have that. We have ones in Santiago, White Sands, New Mexico, Wallops in Maryland, Hawaii, sometimes Australia. We sometimes get those. So when Swift moves over one of these ground stations, it can dump the data that have been collected, and then that comes through the system. And the data initially appear on what we call the quick look site. So once data are on the ground, it takes about 2 hours to be processed and come through the system. Ground station passes can happen every hour or so, but sometimes we have gaps of a few hours when, because of the angle of Swift's orbit, it might not pass one of these ground stations. So on average, you can expect data that have been collected to be available to you after about 5 hours. That's the average. And the quick look site will be updated any time data come down. So I mentioned there were different snapshots. You may have an observation, let's say 3C273, a well-known blazar. Say we were looking at that for 10 kiloseconds during one day. That would be lots of snapshots, and you might get the quick look site updated with one snapshot, and then a few hours later there might be another one. So the data on the quick look site are regularly updated and are not classed as final until they're moved into the archive after 7 to 10 days, at which point the observation will definitely have finished, because any single observation will not cover more than about 48 hours from start to end. Most of them are less than 24 hours, but if it's over a weekend, you might get an observation on Friday and Saturday and Sunday, Monday in one OBS-ID. So the main point of this slide is to warn you that if you're looking on the quick look site and waiting for new data, it can update. So don't think, oh, look, my source is there, but I don't have all the data. It may well just appear later in the day. Okay, so before I tell you literally how to run the software yourself, if you just want XRT data, we actually provide an online product generator at Leicester. So this was written by Andy and my colleague, Phil Evans. So if you have any questions about it, then he's the one that we pass them on to. But so we have this product generator. It will build light curves, spectra, images, give you an accurate position or run source detection for the whole of the field if you're interested. It's at this website, so we sometimes refer to it as user objects. There's also an API way to access it as well if you want to switch things up. And honestly, if you want X-ray data products for point sources, this is the best way to do it. It's so I am going to teach you how to do things by hand, but this is the most accurate way. The Swift team rely on this every day. We all use it, so it's really useful to know how to do these things by hand, but it's quite often you just run to user objects and it will do it for you. So user objects can be used for any of the observations. GRBs are actually automatically analysed by our system. So if you just want to know whether we have a cool light curve for last night's 2 GRBs, you can go along to this XRT_products page, and there are light curves there for every burst that that Swift has looked at. So ones that the BAT, triggered on, but we also follow up bursts from other instruments. So if Fermi has detected something and it's they want us to look at it, the light curves and the results will be there. Likewise, we follow up ones from SPOM these days and EP, Einstein probe. So anything that is officially classed as a GRB will be under the XRT products page. And in fact, we follow up gravitational wave triggers. I'm not going to go into that in detail, but anything that we do follow up from LIGO or LIGO Virgo Cagra is available online here. And finally, as a link for this, we do have what's called LSXPS. the Living Swift XRT point source catalogue, bit of a mouthful if you say it long. Every observation of Swift in photon counting mode, so that's this two-dimensional imaging we have, is analysed, and we automatically have light curves and spectra built for all these sources. So if you want to have a look, I'll use 3C273 again as an example. You can go to LSXPS and look, and it'll show all the data that we've ever collected on that source with light curves. Only in photon counting mode, just to make that point again, window timing mode is not incorporated into the catalogue. But it's all there for you to have a look at if you want to. And papers galore, if you want to read, well, online documentation, if you want to read the really gory details with more stuff than you've ever wanted to know about how it all works. There are those 3 papers led by Phil, one on the light curves, one on the spectra and enhanced positions, and then the last one's about the catalogue, the LSXPS. And just again, to make it really clear, these are the products out of this are completely suitable for analysis. It's not something as, you know, just have a quick look and go, oh right, that might be right, let's do it by hand. They really are good. All right. Oh yes, sorry, one picture to show you what the product generator looks like. It'd be a bit difficult to see because I've shrunk it so you can see the whole page, but you get options of you know, whether you want the spectral light curves or whatever, so you can generate all of them or just one thing. You can get a light curve, something like that. So although the LSXPS only does photon counting mode, the catalogue, this user object will do everything. So it will plot window timing in blue and photon counting mode in red. So this is an example of a nova. This was RS off Yuki, the current nova. In fact, this is the data from 2021, I think. And I've used this as an example just to show you one thing that could be confusing. If you get bright sources like this, you sometimes get these streaks. That isn't saying that there's a jet coming out of RS off. Those are readout streaks, so out of time events. It's so bright that even as the CCD is being read out, photons are coming in, and so you get this streak. So you can, if you run the source detection, it will actually find some spurious sources along there. There's nothing we can actually do about that. So as long as you're aware of this potential problem, and it is only with very bright sources, then you should. All right, so now, how you would do it if you actually do want to run the data analysis by hand. So this afternoon we will go through this. So I'm going to step through the processing and show you how to extract spectra and light curves and things. But I'm actually just going to go explain it on the slides now, so you have a rough idea of what I'll be going through this afternoon. So the main tool, so this is all part of the HereSoft software, and the main tool for analyzing XRT data is simply called XRT pipeline. You actually could just type XRT pipeline and it will prompt you for all the bits that are important, but you can include this, there are other terms as well, but including cleanup equals no keeps the temporary files, and occasionally they can be useful. So it's certainly not vital, but it will keep you a region centered on the coordinates that you give for the source. And that, in fact, that is another thing. You don't have, if you don't know the position of your source, if you don't know the RA index, you can just run it with the default, which is object, and it will take the RA index from the raw data, but that might not necessarily be centered directly on your source. If you know the coordinates, always give them. It makes the calibration that little bit better. I'm not going to go into the details of the wonders of calibration, but if you know the position, always use it, especially if it's window timing mode, because that gets complicated otherwise. So you can tell it only to process the photon counting mode or only the window timing mode for your observation if you want. It's rare that you would want to do that, but you can say data mode equals PC or data mode equals WT if you do want to. It won't overwrite files of the same name by default. So if so, the term is clobber equals no. So that's the phrase that is used for all things like this. It will not clobber files of the same name. So if for some reason you run this the pipeline in a directory and realize you did something not quite right and you just want to overwrite what you've already got, you can either delete the files or you can run XRT pipeline with the term clobber equals yes, and then that would overwrite the files that are there. And a quick thing to let you know, this GTI is a good time interval. So there are specific times where we can collect data and when we can't. Honestly, we shouldn't be collecting data that don't match these. So this says the elevation angle has to be greater than 30 degrees. The bright Earth angle has to be greater than or equal to 120. So bright Earth is basically keeping away from the Earth limb. So we should never be within those limits anyway, so we wouldn't be collecting data. Likewise, if the CCD temperature ever got below minus 102 degrees, I would be, well, you'd be able to knock me over with a feather. I don't think that it's possible to get down to that temperature without the cooler that we that never switched on. We could theoretically get hotter than minus 47 degrees, not if we've got a nice science plan. So the ones that were planned, we tried to keep everything between minus 55 and minus 65. So as Andy said, we do get out of those limits. Anything above minus 50 degrees, the background level gets high, so it's noisy then. So you detect X-rays that are just from the background and are inconvenient. So you see the background level rise if it's above about minus 50. You may still get useful scientific data above minus 50, but it's becoming less useful. And above minus 47, we just don't recommend that you use it. But it is very rare that we get above those temperatures. Okay, so if we did run XRT pipeline cleanup, because, oh, sorry, missed this bit, it's always a good idea to dump your results out to a log file. In case something doesn't go right, you've got the log, especially if you then need to contact us and say, why is this not working? It really helps if we have the log file to see what it was that had gone wrong. So I would recommend always dumping the results out to a saved log file. Otherwise, it just writes to the screen and it will scroll off and you won't be able to see what happens at the beginning. So if we did do that, if we run XRT pipeline, these are the things that it will prompt you for. So I'm using this GRB from back in May this year, just because it had PC and window timing mode and just seemed like a good one when I was putting these slides together, honestly. So this is what you would see written to the screen. So the stuff in the black are the prompts written to the screen. What I've put in purple is me typing in. So I know that this is the RA and DEC of this GRB. It said you can either have it in degrees like that, or hours, minutes, and seconds. It won't work with colons, and you don't put HM and S. You know, well, I can't divide 269 by 15 in my head, but for the DEC, it would be minus 40 space, whatever the minutes would be, space, whatever the seconds. So no colons and no actual HMS or DMS. But generally, you know, decimal degrees is easier. But if you didn't know the position, this is when you could have point or object. So if you don't know it, use object rather than point. It's just better. These are, I'm going to explain what these numbers are in a minute, but you give it the directory path for where your input files are. So these are the ones that Paolo sent you the email saying would be good to download these for when we have a hands-on play this afternoon. The stem for the input files will always be SW and then followed by the OBS ID of your observation. And then you give it wherever you want the output files. So one thing to note is you can't write the output files to the directory with the input files, if you see what I mean. It has to be on the same level or higher. I think that's to stop you accidentally overwriting the input files if you have clobber equals yes. But again, I'll demonstrate that this afternoon if it's not entirely clear. But this is what we have for the files and things. So You do get a lot of files output when you run XRT pipeline, even more if you include the cleanup equals no that I mentioned. But either way, most of them aren't very important. It will create you spectra and light curves. Don't use them. Really, do not use the spectra and light curve that come out of the XRT pipeline by default. It doesn't take any account of how bright the source is, so if it's piled up or otherwise. It doesn't produce a background file. It's basically useless. It was how it was written after launch, and things have been much better. So if you want something to be done automatically, use our user objects page. If you want to do it by hand, then that's what I'm going to be showing you. So this is an example of an event list. As said, they will all start with SW. You then have an 11-digit number, and that's the OBS ID that is unique to your observation. But within that 11-digit number, the first 8 digits, and they will always, I think, start with at least 10. I don't think we've run out of target. So yeah, the first 8 with 1 or more zeros included at the start, that's known as a target ID. That is unique to the source. So any observation that you see that starts 01310284, anything with that will correspond to this GRB 250504A. Then there may be more than one target ID for a given source for various reasons, but any given target ID will only correspond to one source. The last 3 digits are known as the segment number, and this is because we observe most sources more than once, honestly. So for a GRB, the first observation will start 000. For anything that isn't as GRB, the first observation would be 001. And you go 002, 003. Occasionally, a number will be skipped. It doesn't mean anything. It's just how the science planning happens. And very occasionally, the numbers will not be in chronological order. So you could have 001. The next one is 003, and then it goes back to 002. It's just a quirk of the science planning software because they have a lot of observations to juggle, and the automated system just sometimes moves things around. So don't be surprised if you look at it and think, okay, so the science planners can't count. It's not them, it's the software. So that's all that. 11 digits is the OBS ID, 8 digits is the target ID, 3 digits is the segment number. We then, for an XRT observation, it will then be followed with an S. If it's UVOT, as we will see after the copy break, it's a U, and it's B for that. It's all fairly logical. You then have 2 letters that show you which mode you're in. So these days, it's going to be WT for window timing mode or PC for photon counting mode. We did collect a few data sets with the photodiode mode that Andy mentioned is now disabled. That was disabled from May 2005, so only, well, 6.5 months after launch. And we didn't observe many things in that, but there are 1 or 2 data sets in the archive where you would see PD for it's LR for low rate photodiodes or PU piled up photodiode, but it's unlikely you would ever need them. The next 2 are the window size. As a user, the difference, it doesn't make any difference to you. Basically, for the PC mode, which is the one over here, the full window is 600 pixels by 600 pixels, but sometimes we have what you call them, calibration sources in the corners that we've sort of changed the size of the windows to get more or less of the calibration sources over time. The calibration sources are masked out for normal science data, so you guys won't see them. But we've sometimes had, I think the smallest window we have is actually, what, 500 pixels, maybe 480? Yeah. Most of the time, the targets you want are going to be in the middle of the field of view anyway. You won't notice these extra pixels, more or less. And 1 pixel is 2.36 arcseconds. Yeah, but my point of saying this is that there will be a W and then either 2, 3, or 4 for window timing mode, and W3, W2, W3, or W. Actually, yes, the same W's, same numbers for PC mode. They just are referring to different sizes. And then we have 2 letters. You will see either PO for pointing or SL. ST for slew and settling. You can't analyze the slew and settling data, so you'll only ever want the PO for pointing. And then finally, we have the CL.EVT, which tells you it's a cleaned event list. The raw data that you have before you run XRT pipeline will be either UF.EVT, so unfiltered, or for window timing mode, you can have, there'll be UF and UFRE. Which is to do with reconstructing things, but the only useful data for you guys is the CL.EVT cleaned event list. All right, so once you have your cleaned event list, you probably want to extract a spectrum or a light curve or even just an image to see what it looks like. And what we use for that is a task called XSelect. This is not unique to Swift. XSelect was, I think, written in the 80s. It's a lot older than Swift. It can be used for all kinds of X-ray missions, honestly, but it does what we want for Swift. There, because it's old and well-developed software, there's plenty of documentation if you ever do actually want to read about the stuff that I'm not going to tell you about today, because there's even more things that you can do if you want to. But you just type XSelect to get it started. It will ask you for a session name. This is, it's a way that you can read things back in afterwards, but it doesn't actually do anything useful to my mind. So you have to give it a session name, but I'm not going to tell you how to read the session back in because I don't think it's a good idea. So you can type things on whole command lines, but I've done it to show you what it will prompt you for if you just do some things. I've also tried to, I think I've remembered to do it. I've written out the words in full here. You can abbreviate almost everything. So read event could be abbreviated to RE space EV. If you said RE space E, I think it would point out that E could stand for more than one thing. So if you try to do something that is ambiguous, it will tell you. It'll say, no, you've got to give me more information. But if you've done this enough times, you don't type the whole words because, you know, typing takes time and your fingers get tired and all kinds of stuff. But here I have tried to write the whole word so that you know what it is it's saying. So if I say read event, it will then say, which directory is your event file in? I tend to run these things in the directory where the files are. You don't have to. You can give it a whole long path length to where things are, but I tend to find it easier to run it in the directory. So // or just dot means do it right here. Then it'll ask you for the event list. So we're going to start with window timing mode here. While that is to some extent the slightly more unusual, maybe even slightly more complicated to look at mode for Swift. If it's a GRB, which is what we're doing here, we almost always start in window timing mode before going to photon counting mode, so it makes sense to do it through chronologically the order the data are collected. So when you say it's this, it says, oh, got new mission Swift. Swift should not be capitalized, ever. It's not an acronym. Why on earth XSelect decided to, it makes me want to punch my computer every time I see this. Please don't capitalize Swift. It's named after the bird. It moves quickly. It's not an acronym. We have occasionally come up with ideas for what it could be as an acronym. Those are a little too rude to be shared here. Ask me later if you want to know. I'm not being recorded saying what they stand for. Anyway, it says, it's Swift. Do you want to reset the mission? Well, there's no reason why you would not want to reset the mission, so say yes. And then it writes this information here. So it tells you what the OBS ID was, tells you the date of the observation, it tells us that we're using window timing mode. In this case, the very first observation of a GRB often is just called burst and then the bat coordinates. Later ones, it will actually know what the name of the GRB is. So, first thing you probably want to do, or the first sensible thing to do, is to extract an image. So, the command is extract image. And it writes this stuff to the screen, so it shows you what the exposure time is, how many photons there are. So this good, the number under good is how many photons there are in the image. And then you have to say plot image. XSelect plots things in DS9, so you always have to make sure that DS9 as the image viewer is installed as well, because it's not actually part of HereSoft, but it's very easy to install. So we've done, as I said, we've started with a window timing mode thing. Now, this is not the easiest thing to see on a screen like this, so I have zoomed in slightly here, and you can see it is, in this case, just a single strip. And that's because the window timing mode, the CCD is basically collapsed down to be read out. So it reads out, collapses down 10 rows, reads them out, and recombines them. So all you see is a strip. It doesn't mean that we're not using the whole CCD. All the data are there. It's just being compressed down to allow us to read it out more quickly. It's why WT mode has the higher time resolution, 1.7 milliseconds. So the green circle is just me showing you where the source is, because on screens like this, it's not always quite as easy to see. The angle it's at is the roll angle of a spacecraft. So Swift has big solar panels, and they have to point towards the sun, and that can lead to, you know, different angles it has to be at depending on where it's looking in the sky. And I've just realized I'm doing that on camera. I'm being filmed. Okay. Anyway, the angle is the roll angle of the spacecraft. So you can see different angles. So sometimes it will be completely vertical, sometimes it will be completely horizontal. So it's just the roll angle. What you sometimes get is that. So this just means that we have had a lot of observations and they've all been at different roll angles. This is an extreme example. This is RS Ophiuchi again, so the nova I mentioned earlier. But this was actually the first time we observed RS off, which was back in 2006. And at that point, we wanted to observe it every orbit for 48 hours. And it ended up with lots of different roll angles. So you can get this kind of pretty pattern if you do. You usually these days wouldn't get more than maybe 2 or 3 different roll angles, but that's, if you see the different things, that's why. If you run XRT pipeline with the coordinates of the source, which is what I recommend, as I said, especially for window timing mode, the different windows will cross at the position of the source, which is, well, that's what you need basically. If you've got multiple roll angles and you're going to try and analyze them, all the different snapshots at the same time, you really need them to cross at the position of the source, which is why, again, giving the coordinates is very useful when you're an XRT pipeline. So just going back to there, I should have said, you can use, you might think it's a bit weird to use a circle when it's only a strip to extract your source, but it works fine. The software knows what it's doing, and it's easier to draw circles rather than draw a box and then have to get the roll angle right. Obviously, circles are symmetrical, so you don't have to worry about the roll. But if you have something like that, then what do you do for a background region? I mean, for something like this, you can just take a little circle, and if you want, you just move it along the window away from the source, and that would be fine. But if you have something like that, over here is a useful background for when it was at that roll angle. But if you draw a circle there, the ones that are at that roll angle would completely miss the background region, which isn't helpful. So Andy actually came up with a handy way to get around this. So this is basically here for reference. It's on our website. I'm not going to go into the details now. It's something that's much easier to read and then try rather than just read what it says there. But the information is there. assuming these slides will be made available somewhere. If not, it is on our website. But if you want to have a go this afternoon and it doesn't make sense, let me know. But going on to what else we might want to do with XSelect, well, we've got the image. That's all we've done so far. You probably want to do a light curve or a spectrum, and what you want to do is tell it you just want the light curve for the source of interest. So you don't want a light curve for the whole field of view, you just want centered on the source. So that's why we are defining source regions. So popping back up to that one again, I had defined this circle centered on the source region. We'll come on to what to do if it's a very bright source in a slide or two. So you define the source region within DS9 in your image, and you save it because you then have to read it into XSelect. And the commands will be filter region, and then whatever you've called your source region. Make sure you always save your source region in FK5, so the world coordinate system. So it's saved as RA and DEC, not in CCD coordinates, because the source can move its position in the CCD if you have a second observation. But if you have it saved as RA and DEC, which is a sensible thing, it will always be in the right place. So if we wanted to extract things in our source region, we'd say filter region source.reg. At that point, everything we do is only the data in that small source region until you get rid of it. So you don't have to say filter region, extract a light curve, and then if you want to extract a spectrum, you don't have to do the filter region again. It remembers it until you say clear region, at which point it deletes it for you. Sticking with a light curve, the default bin size for a window timing light curve is 1 second. For photon counting mode, it's 5 seconds. You might want something longer or shorter. You would, to do that, you'd say set bin size and then give it in seconds. I'm going to be showing you how to correct light curves for various reasons shortly. You can't correct a light curve directly if the bins are longer than 10 seconds. So you could correct a thing for 10 seconds and then you could, there are timing analysis tools outside XSelect that could then bin up your light curve further if you wanted to. So the absolute shortest bin size you could go to for window timing, we said the timing resolution is 17 milliseconds. I think it's 17 point something. Yeah. The shortest that XSelect will allow you to use is 18. It's 1.8, not 17, 1.7, 1.8. It will, if you try and do something shorter, it will tell you off and say, no, I can't go shorter than 0.0018. And for PC mode, it's just over 2.5 seconds is the shortest that it will let you do. So if you extract the whole, if you don't do any energy filtering, you get 0.2 and a bit kV up to 10 and a bit kV, but XRT is calibrated from 0.3 to 10 kV. So that's the energy range that you would be fitting if you were fitting a spectrum, which will be later. It's generally not advisable to go below 0.3 kV. However, everything is done in terms of PHA channels, not energy. Now, one channel is 10 EV for Swift. So if we say we want 0.3 to 10 kV, we would say filter PHA cut 30 to 1000. So 30 channels means 300 EV, 0.3 kV. 1000 channels is 10,000 EV, 10 kV. So there's this factor of 10 that you have to remember if you're doing energy filtering. So after that, we can say extract curve if we want to extract a light curve, and then plot curve because it won't plot anything for you directly, and it will open it up in an X window. And here we have an example of a light curve that's in 2 different snapshots. So we had to stop observing in window timing mode at about 750 seconds thereabouts. That will have been Swift slewing away, I think, potentially moving into PC mode. I can't think what full light curve for this GRB is like. But I chose this so that we could see what two different snapshots look like. And you might just want to do something on a single snapshot, and I'll show you how to do that in a minute. If you've extracted your light curve and whatever, XSelect does not save anything by default. So anything that you want to save and then do other things with, make sure you do type save curve, because if you extract something else, it will come out of XSelect and you haven't typed save, then you've lost it. So always save your work. So say we do just want this first snapshot, for example. If we wanted to filter just on this, there are multiple ways that you can do it. So the command is filter time, and then you tell it how you want to define the time region of interest. So you can say filter time cursor, and then it would pop up and you would click in the start and stop time that you're interested in. So in this case, any of the white bits, it knows there are no data. So let's say that we wanted to filter on this snapshot. If you type filter time cursor, you click before the red points start. So again, I'll show this actually manually this afternoon, but you would click before they start and after they stop. So you don't have to click on the absolute first red bin. You just have to click before it starts and after it starts, and not in any other data that might be getting in the way. Alternatively, if you don't want to rely on clicking with the cursor, you can say filter time SCC. So that's short for spacecraft clock. So in this case, let's say we didn't want the whole of that first snapshot. We wanted to filter from 200 seconds to 400 seconds. And you would say filter time SCC, and then when it prompts you for the numbers, you would say 200, 400. And that's all. It's not time after burst, it's time after the start of the observation. So it's because it doesn't know, it just knows this starts at 0. We know that that's actually, I don't know, 60 seconds after the GRB or whatever. It just knows that the XRT observation started then. Ooh, sorry. You can also filter on a time file. So if you're doing something, an observation that's coordinated between instruments, and you know exactly what time, I don't know, SWAM, for example, you know exactly what time they observed, and you wanted a Swift observation exactly the same, assuming that we did have data at the time, you get a GTI file and you can read that in to make it match. Again, more details in the documentation or this afternoon if you need it. So we extracted a light curve back here, and for that we did this energy cut. However, now we want to extract a spectrum. Make sure you don't have an energy cut there. So if we'd done it for the light curve, we said filter PHA cut. We would now want to clear the PHA cut before a spectrum. And that's because you need the full energy range to match with the calibration files. If they don't match up, it will, when you read it into XSpec, which is what we use for fitting spectra, it will throw a fit and say it doesn't match, and you have to go back and do it again. So always make sure, do not use a PHA cut command before extracting a spectrum. And again, you have to save a spectrum, or save if you're making a spectrum. And as I said, this is suitable for fitting in XSpec. There are other spectral fitting packages. XSpec is the only one I really know, so that's the one we're talking about, but there are other things that could be used if you wanted to. We have the calibration files that would be used with them. One thing to note, we have grade selections. So If a photon comes in and hits a CCD pixel, if it just hits a single pixel, that's known as a grade 0 event. But sometimes the photon energy might spread over 2 pixels or 3 pixels, and these are different grades. For XMM, they're called patterns. So I'm guessing the XMM guys will mention that tomorrow. But grades and patterns, they're actually defined the same way. So for photon counting mode, everything is calibrated either for grade 0 to 12 or grade 0 and also grade 0 to 4. For window timing mode, it's either grade 0 or grade 0 to 2. There are reasons why you might not want to use all the grades, but generally it's probably best to stick to grade 0 to 12 for photon counting mode most of the time anyway. So we've got a spectrum now. I like having a spectrum from XSelect, so we're going to come out of XSelect. Well, actually, just to show you a plot of what it looks like. If you plotted, did I say to plot spectrum? No, I didn't. But if you did plot spectrum in XSelect, you don't have to plot any of them, but if you do, it looks like that, which is sort of, well, yeah, there are clearly X-ray counts. Again, it's in channel energy, so 0.3 kV is about there, and that's 10 kV. You can't fit the spectrum in XSelect. That's why we have to save it. It'll come out to XSpec. Once you do the bits that I'll show you shortly and read it into XSpec, it looks much more like a typical X-ray spectrum that you might see in papers and things. So that's the example spectrum, and I said prettified because I made a nice plot. Okay, so I mentioned in passing that we might want different source extraction regions. So I just used a circle for that window timing mode. We have this issue potentially called pileup, and you mentioned it in passing. So what we really want is an X-ray photon to come in, be registered in the CCD, and be read out. So we know exactly what the energy of that photon is, what grade it is, and everything. However, for bright sources, you might get 2 photons hitting either the same pixel or adjacent pixels before the CCD has been read out. And the software doesn't realize it can't know that that's 2 separate photons. It thinks it's just 1. So instead of having 2 lower energy photons registered and read out, it will think it's 1 photon with the combined energy of the 2 that came out. This is known as pileup. It can be a problem for all X-ray missions, I think, certainly lots. XMM for tomorrow also has the issue. So you have to know whether it's going to be a problem. So you need to check to see if data are piled up. So the method I'm going to show you here is what to do for photon counting mode. For window timing mode, basically you just exclude data. Well, so that's I should take a step back actually. Point sources have what is known as, well, everything, but we're talking about point sources, have this thing called the point spread function. So although you know it's we think of it as a point source, it will be spread over a number of pixels in the CCD. So right in the core of the PSF, point spread function, is where you get most of the photons, and then it sort of spreads out further. So the core is where the pileup will be a problem if it's a problem. If you just exclude the core, and you can then correct for the lost counts using the calibration files, and then pileup is not a problem. So if you don't correct for pileup, the shape of your spectrum will be wrong. So instead of having, as I said, as my basic example, 2 low energy photons, you might get 1 high energy photon. So instead of knowing that you had 2 photons that were both, say one was 1 kV and another was 1.5 kV, instead of having 2 photons there, it'll think you've got a single photon of 2.5 kV. I'm oversimplifying, but that's more or less what happens. So instead of having 2 photons there and 1 photon, you get 1 photon there. So that flattens your spectrum. So you're getting apparently more high energy counts and fewer low energy counts. So your spectrum ends up flatter or harder. And obviously that's not what you want. You want to know what the actual shape of your spectrum is. So that's why we have to correct the pileup. If it's really extreme pileup, you can even lose counts. You know, it's so much that it's, I mentioned we had grades 0, 0 to 2 for window timing, 0, 0 to 4, 0 to 12 PC mode. Grades are actually calibrated in PC mode up to 31. If you get, well, 31, they're defined up to 31. If you end up with photons moving outside, then you actually apparently lose. You just get holes in the data. Long story short, if you have pileup, you need to correct for it. So for window timing mode, basically you can just draw an annulus and exclude the core until the count rate is less than about 100 or 150 counts a second. And that's because what I'm about to show you for photon counting mode, you can't do for the one-dimensional PSF that we have for window timing mode. So for window timing, basically you just want to bring the count rate down below about 100 to 150. PC mode, we can do it more accurately. So pileup in PC mode becomes an issue round about 0.6 counts a second. So anything that you think might be too bright, that's when you need to start doing things. So what you do is you extract an image for the time of interest, and you read it into this task called XImage, because this allows us to fit the PSF to the data and see where our data diverge from what it should be. And that will show you where pileup is a problem. So I've extracted an image. In this case, I've called it PC1 because it's from a first snapshot of PC mode data. Read it into XImage. And in this case, CPD means change plotting device. There's a very handy one called XTK. It's only available in XImage, but it means you can zoom in on the data and you can move it around. X windows, which we use in XSpec and in XSelect, is fine, but it doesn't let you reposition things. So XTK is very handy. The one irritating thing about XImage is you don't say plot, you say display. Everything else, I think, uses plot. XImage doesn't. So we need to get an estimate of the background count rate before you do anything by typing back. Sometimes, if you forget to do it, it may still work, but sometimes it can't. When you do the PSF detection, it sometimes just can't average the background properly. So if you type back, it should make it work otherwise. And then what we say is PSF/cur. So PSF/cursor. And what you do is you click right in the center of your source, and then where it looks like the point spread function, the PSF has faded into the background. So it's probably going to be about 30 to 40 pixels out. If it's a really bright source, you might want to go a bit further. And you get an image like this pop up. The only bit of this that we're actually interested in is the bit in the cyan points. So this shows you the encircled energy fraction. Basically tells you that if you're out at 30 pixels, then you've got about 90% of the point spread function, but it's just plot that. It's not important for the pileup detection, pileup estimation. The only thing that is the cyan points. The magenta line is some random attempt by XImage to fit the PSF. Ignore it. You don't want it. This is the actual point spread function for Swift. Don't worry about, it's a combination of a King function and a Gaussian function. You don't need to worry about all of this because we have a nice little file with it defined in that you can download from our website, fit to the data, and see where it diverges. So this is what we do. This is the file, and it's a COD file. Can't remember what COD stands for. Never mind. The only thing is, they have to be written in reverse Polish notation. I have no idea if any of you have come across that before, but it's evil. But it's been written for you, so you don't need to worry about this. So what you do is you ignore the the center of the PSF, the bit where you think it might be piled up, ignore all that and go a bit further out, and then fit the PSF, fit this PSF.cod file to what you see, and then extrapolate inwards. It won't be absolutely perfect because you've got background in there. The PSF is, you know, just for the source, but there are background counts. So don't be surprised if you sort of get a few wiggles like that. But pileup will look like that. The data will be consistently, noticeably below your line. So that white line is what the PSF would be if it weren't piled up. And the cyan points are what we are seeing in this data set. So where they diverge, that's the point at which pileup is a problem. So in this case, it's 10, 11 arc seconds. It is an approximation, so if you're really concerned about pileup, probably better to exclude a little bit more. So this is given in arc seconds. I tend to do everything in pixels, whole numbers of pixels. It doesn't matter, you can work in arc seconds. And as I mentioned in passing earlier, that's the conversion. 1 arc second is 2.36 pixels for XRT. And as I said, for window timing mode, you basically just do an annulus and exclude the core. So we've excluded this core, but I mean, obviously that means your count rate is going to be wrong because you're ignoring most of the counts. So what we have to do is correct for this by using, for spectrum, you use an exposure map. So this corrects both for pileup, well, it's the ARC corrects for pileup. Sorry, I'm jumping ahead. This corrects for bad columns. So Andy mentioned that there was a micrometeoroid strike in 2005, and that led to damaged parts of the CCDs, why we can't use photodiode mode anymore. So we have these, see the darker lines here, there are rows, columns of pixels have been masked out from the CCD because otherwise they would just saturate everything. They're constantly bright. So we have these masked out. But if your source lies over one of those, again, you're losing counts the way you did for using an annulus for pileup. So we have to correct for those. And that's where the exposure maps come in. We have to, you need an exposure map for the exact same time interval as for your the spectrum that you've extracted. If it's just the whole of the observation, then there will be an exposure map ready generated when you run XRT pipeline. If you want just one snapshot or some combination, then you have to run, you have to create an exposure map running XRT Expo map. But before that, you need an event list to match that time interval because the exposure map is generated from an event list. So in XSelect again, you would say extract event this time rather than spectrum or light curve. You also definitely need this bit, copy all equals yes, because otherwise it loses the information about the bad pixels and it means your exposure map won't work. So extract event, copy all equals yes. And then XRT Expo map is the tool that will build you an exposure map that you want. I'm not going to read this out. Again, it's on the slides for reference. But what we need is this exposure map. You can, if you have an observation, if you have a spectrum that's more than one observation, you will need to combine exposure maps because they can only be generated for one OBS ID at a time, but you can add them up. But once you have the exposure map, what you do is create an ARC file. So these are the ancillary response function file. I can never remember what the F is. Ancillary response file, not ancillary response function file, ARC file. Anyway, well, yes, I might not have got it right. So the ARC, there are two different calibration files that are needed for any XRT spectrum. One is the RMF, the response matrix. Those are in the calibration database. Those are created in the past by Andy, these days with Andy and some people who are working with him. So that is not unique to the observation. The ARC is unique to the observation. So you have to build XRT, run XRT makeoff to build an ancillary response file for your spectrum of interest. And again, it will prompt you for most things, but you do need to give it the exposure map. When it asks for the source X and Y coordinates, if you just say -1, -1, it will work it out from the spectrum, and that's much easier, because otherwise you have to look in your image and read off the CCD coordinates. It's not even the RA and DEC in decimal or anything, it's CCD coordinates that it needs. And it's very easy to get that wrong. But if you say -1, it reads it from the header of the spectral file, and so it will be right. Okay, so that is how you would build an ARF. It will write a whole load of stuff to the screen. Useful bit is it will tell you what, it will say the percentage of fluence within the ROI, so that's region of interest. So it tells you that we've used an annulus to exclude the core of the PSF because it was piled up, and we've still got about 73% remaining. What we would, in order to correct it up for the lost counts, the number would be 100 divided by that. So the factor, we need to multiply the count rate, if you need to know the count rate, by a factor of, in this case, 1.356. But the ARF, when you're fitting a spectrum, the ARF is incorporated into when you're modeling. So if you get a flux from your fit, that is correct. The ARF will correct the flux for you automatically, but XSpec writes a count rate to the screen, and that is not corrected because it doesn't use the ARF when it's just the raw count rate from the spectrum. So if you need to know what the count rate is of your spectrum, you need to know what that correction factor is. So when you have a spectrum, you need to get it in the right format for fitting in XSpec. And there's this task, GRP PHA, short for group PHA. Spectra are either called .pha files or .pi files. These days, they're basically, the names are interchangeable. In fact, XMM, I think, tends to call them underscored, well, .ds for some reason. That's what, yes, I think it is, but why? Why call it data subspace? Does that sound like a spectrum? Well, I mean, I'm not sure PI and PHA sound like spectrum, but they are. But that's where the name group GRP PHA comes from. So you give it the name of your spectrum. If you want to overwrite it, you put an exclamation mark before the name. You can give it a different name if you want, but otherwise it's like that. And then there are certain things that you need to set up before you can fit a spectrum in XSpec. I mentioned that it's only calibrated from 0.3 to 10 kV. So what we do is set everything below 0.3 kV to bad. So it will ignore those. In the past, many people would fit spectra using chi-squared statistics and say you should have at least 15 or 20 counts per bin to be able to do this. You can, but honestly, these days it's generally recommended that you use cache statistics. It's called CStat in XSpec because it's less biased, even for faint sources for which cache statistics were always used. So always use them for faint sources, but even for bright sources, we would generally recommend that you use cache statistics. That ought to be unbinned spectra, but XSpec has this slight oddity that you need to have at least one count per bin for it to be accurate. I think it's, I don't know if it's the errors or what, but Keith Arnaud, who is the XSpec guru, says you need at least one count per bin. So you'd say group min 1. The other thing to do is we're changing the keywords for the files so that when you read your spectrum into XSpec, it will know what they are and it will read them in automatically. So that's that. We're not going through how to fit a spectrum this morning. If anybody, we can do it this afternoon. I know some people have experience with X-ray astronomy, some people don't. So we can always go through how to fit a spectrum in XSpec this afternoon. So that was correcting for a spectrum. Correcting a light curve, there is actually a specific task called XRT LC core. So this is specific to Swift. Group PHA and things are not. That's like X-select, that's for everything. But XRT LC core, as long as your light curve bins are no longer than 10 seconds, that's what I mentioned earlier, as long as they're no longer than 10 seconds, you can correct them using this XRT LC core. You can either run it so you get a correction per snapshot, which is usually accurate enough, but otherwise it will give you a correction every 10 seconds, which is why your light curve can't have bins longer than 10 seconds. Occasionally, Swift might have drifted during the orbit and the correction factor would change if you drifted over a bad column or away. Most of the time it won't, so usually you don't need to bother. So you could just include this PC end frame or W2 end frame equals 0, and then the output file will have one correction per snapshot, which can be useful for various reasons. So it will prompt you for everything, and then you will end up with a nicely corrected light curve. You probably want to do background subtraction of it though. And again, this LC math tool is not Swift specific. This has been around for many decades. I mean, Swift's been around for 2 decades, but LC math many more. And you would give it the input corrected light curve, so the one that you got out of XRT LC core. You'd give it your background light curve, give it an output name. The scaling factor for input is always 1 because it's already been corrected in this case. But if you used a different size background region for your background light curve, you need to scale it here. So usually, certainly for PC mode, we would recommend you use a larger extraction region for your background than your source, because the background does vary a bit over the CCD. So if you use a bigger one, it's a better average. In this case, I used a background region with a radius of 60 pixels compared to 30 pixels for my source, and so the background region is bigger, so you need to scale it down. You just give it the ratio of the areas. So I just used a circle. If you can use a background annulus if you want, but then you have to work out your area, and it's much easier if it's a circle, because you know, pi r squared and all that, rather than pi r squared minus a pi r squared. So that's why the scaling factor is 0.25 in this case. And I think, yeah, that is right on time, I think. Yes, 11 o'clock, look at that. So that's where we're stopping now. It's coffee break time, I believe. We've lost Paolo, but Giancarlo is kind of in charge, I suppose, in this room right now.